My name is Avi, and I'm a PhD student at UC Berkeley. I will be talking about some of our recent work on accelerating RL through data-driven behavioral priors. Let's consider a typical RL problem. A robot is placed on a table with several objects, and it begins to explore this environment for high-reward states and actions. Since the agent is initialized without any prior knowledge, it must try many largely unproductive behaviors before it discovers a high-reward outcome. Humans rarely attempt to solve new tasks in this way. They draw on their prior experience of what is useful when attempting a new task. When faced with a task involving objects on a table, a person might grasp an object, stack multiple objects, or explore other object rearrangements rather than relearning how to move their arms and fingers. We propose to speed up learning of new tasks through behavioral priors. Our method, which we call prior accelerated reinforcement, or Parrot, takes as input a large dataset of near optimal trajectories from a diverse range of tasks and learns a prior. Given a new task with previously unseen objects, we use the prior to explore effectively and learn a policy that maximizes the reward. We now describe the mathematical form of the prior. The behavioral prior is a function f that takes as input state s and a random noise z and outputs an action a that is likely to lead to useful behavior when executed. Note that z's are sampled from a simple distribution such as a Gaussian and get mapped to meaningful actions by f. However, there may be many possible useful tasks that one can perform in any given environment, and the prior alone will not necessarily maximize the reward for our task of interest. We combine the behavioral prior with a policy pi, which also takes the current state s as input and outputs z, allowing the policy to control the action executed in the environment. This essentially transforms the MDP that the policy is trying to learn into an easier one, since any random action will be transformed into one that is more likely to lead to higher rewards. We utilize flow-based likelihood models to train the prior as they satisfy several attractive properties. Flow-based models can transform samples from a simple distribution, such as a Gaussian, to complex multimodal distributions, and they allow conditioning the sampling process on additional information, such as the current observation in the environment. We train the model to maximize the conditional log likelihood of actions observed in our training dataset, essentially learning a generative model over actions from past tasks and use it for accelerating learning of new tasks. We evaluate our method on a suite of robot manipulation tasks involving previously unseen objects, image observations, and sparse reward functions. Parrot substantially outperforms baselines such as initializing from behavior cloning and prior works in hierarchical imitation and reinforcement learning. Thank you.